Okay, maybe yeah. I'll just start with just a couple logistical things. Um, so, you guys are all here, and that's great. I've got students who are like begging to get into this section. I'm not comfortable with continuing adding students beyond the capacity of our classroom, and also we have readers and TAs assigned to do the grading, and there's 3 lectures of this course open, and another lecture meets pretty much at the same time as this, and I understand you guys maybe prefer to take the class with me for whatever reason, but the it is unfair to my readers to keep adding students to grade and things like that. To say now you have to grade 84 and 83 or whatever, however many people, whereas the other reader might only have to grade 40 students or 30 students. And so, if you can find someone, if you really want to get into this lecture, you might be able to find someone who's willing to switch into an open one. They just added a few more seats in my second lecture, which meets at 2. Pretty much the same content there. I have students asking if they can just switch and just go to the other lecture for whatever thing. I prefer if you go to your own assigned one, but I can't enforce that. And the only quote threat to you is if I happen to take attendance on a certain day and you're not present in your assigned lecture, then you'll miss out on your attendance point. But that's a small penalty for whatever convenience or thing that you might gain. But anyway, you are free to go as you please. Okay, today we're going to continue our discussion on data structures. So we left off on Monday. We talked about vectors, atomic vectors, and lists, and then just a few attributes such as names. So atomic vectors, we looked at the different types, coercion, lists, and then as far as attributes go, we just covered names. Okay, and so there are other attributes that are useful, and here we have something called levels, which create factors. Okay, and so a factor is it's a vector, and it can only contain a certain set of values. Okay, and here if you create a factor such as this a b b a, and you print it out, it comes out a b b a, and it looks almost like it's a character vector. But if you ask R what the type of this thing, what this is, it's going to actually say it's an integer vector. Okay, so it stores these things as integers, and in a separate thing it says these integers take on these values. Okay, or these levels. Okay, the levels are assigned to the integer values. Okay, so I have this in the thing here. It says type of is integer, and the levels are a and b. And so if you put this and you say as.integer, ask for x, it's going to say, oh, it's actually just the numbers 1, 2, 2, 1. Okay, and you can of course if you say type of for x, it'll say integer. Whereas I think somebody might have asked the question about what is class. Class is a object type, S3 object type, and it will say factor. But as far as how these things are stored, it's an integer. Okay, and then the levels associated with this is x. Okay, so you can also ask attributes of x, and it will say we've got these different attributes. This is the level, and this is the factor. Okay, oh, I forgot. Let me blow up my okay, so we got so factors are integer vectors with levels that are assigned to each of these things. Okay, and so if you try to put something in there that is not one of the defined levels, it's going to complain. Okay, so if we have x and you try to replace the second element in x with c, it's gonna complain. It's gonna say that is not allowed. Okay, but of course you can stick back x there, and then again, if you ask as.integer x, it now puts it in there. Okay. Okay, and an important thing is you can't combine factors in the same way that you combine other things, because again they are underlying integer vectors, and so when you combine them, you're essentially trying to combine integer vectors, and then you lose the associated levels. It's the factor. This factor thing is not just using the command C is not smart enough to say, oh, I've got to figure out, what set of unique levels exist, and then remap all of the values that way. Okay. All right. So it says factors are useful when you know the possible values a variable may take, even if you don't see all the values in a given data set. Okay. So using a factor instead of character vector makes it obvious when some groups contain no observations. Okay. So here, let's say you want to create a factor for sex, and in this example, we're just simplifying things and just saying we have male and female. I realize it's more complicated than that. But so, let's say in your data you've observed 3 males. If you just do table of the character vector, okay, where it kind of tabulates. So the table function will tabulate values that it sees. It'll say, oh, I see 3 m's. Okay? Whereas if you define it as a factor and you say the levels that exist that we have are m and f, and I suppose we could throw in another one for non-binary, and then that would show up here. Okay? We would have 3 and 0 and whatnot. Okay? And so this makes it clear that we have other levels even though we don't have any observations associated with those other levels. Okay. When you read in a data file, okay, so you're bringing in a data file, one of the default things is that, or actually, you've got a bunch of different things, all right. Maybe you're expecting something to be a numeric vector, and instead it produces a factor. Okay, and this is very problematic because you might you want these things as numbers, but then it got turned into a factor, and so when you do mathematical operations, okay, so here I've got x as my factor, and then let's say I didn't realize it was a factor. And you start doing mathematical operations, it's gonna get angry with you, right? Or not angry, but it just says this is not allowed. And so and oftentimes the problem there is that maybe you have a missing value in your column of values that you're importing, and rather than leaving it blank, there might be a character like a dash or something else printed there to indicate that this value is missing. Okay, and then so when R is reading this, it says, oh, these aren't actually numbers. We have something we have a character in here. Okay, now that there's a single character, I don't know what to do. I'm going to turn this whole thing into a factor. Okay, and so so it coerces the vector from factor to and turns it into a factor. And so one way to fix this is you coerce the vector into a character, then and then from a character into a double vector. Okay, so let's say I don't know. Okay, so let's. I'm creating a character. We'll do 1 through 10, and I'll just do as.character. Okay, and then so I've got y is this, and then I'm just going to replace the fourth element of y with a dash, right? Okay, and then so if we look at this, and then if you were to import this, and you create factor of this, this is not what we want, okay? And and then if we were to try to do math with this, it would get angry with us, okay? So this is probably not what we want, okay? But we have this, and so in order to fix this, you got to kind of reverse the things, and you would say as.character. You would turn the factor into this, and then you would have to replace. You'd have to do the fourth element of z is now an NA, okay? And then so this is. I'm sorry. We have to. Sorry. As.character. We should have this, and then we do the NA, and then now we can do as numeric, okay? As numeric, or as integer, or as double z, okay? And then it figures it out. All right, and it says, of course, a much better plan is to discover what caused the problem in the first place, and use that as the NA strings argument in the read.csv. So when you're using your read.table or read.csv, there is an option to indicate if you see this symbol in there, use that as the symbol for missing value. Okay. And then the other part is we have strings as factors. Okay, this is a kind of a default feature if you look up the function read.csv. So when you're importing data, read.csv, read.table, these are kind of your default things. One of the settings here is strings as factors. The default setting is true. Okay. Now on your computer, you could change the default thing from being true to false. Okay. However, what this will cause is it will cause your code to break on other machines. Okay, because other machines will have different default settings. So in general, it's not a good idea to mess with your the default settings on your computer. Okay, because when you'll get things used to you'll get used to doing things a certain way on your machine, and then when you do it on someone else's machine, it breaks. So rather than changing the default setting on strings as factors, which is default true for most people's machines, it is better to explicitly say strings as factors false. Okay, and that's going to take strings and import them as character data. Okay. And then if you want to turn your character data into a factor, that's up to you. But that's what we have, okay? Yeah, and it says this is suboptimal because there's no way for your functions to know the set of all possible levels, okay? Which is true, or their optimal order. Also another thing for factors. A lot of times with factors you have kind of an ordering of the factors that we would prefer. Okay, and just to reiterate, factors look like character vectors, but they are actually integers, and so just be careful when treating them like strings. Some string methods we won't really use gsub or grep. Will coerce factors into strings, while others, such as n characters, will throw an error. Okay, and then things like combine and your C will use the underlying integer values. Okay, so just to reiterate, it's best to explicitly define your factors yourself rather than letting R try to do it for you. Okay. Yeah, and the reason why this is, you know, R was developed back in the days of Bell Labs a long time ago, where, you know, you had computers with limited memory, okay, and it was advantageous to turn things into this integer form as far as storage in the memory system goes, okay. Now it doesn't really matter. We can treat things as characters, and it's fine. Okay. All right, let's talk about matrices, okay. So matrices, essentially, they're just atomic vectors with a dimension attribute, okay. So you can create something with the matrix command, okay. And so it says adding a dimension attribute to an atomic vector allows it to behave like a multi-dimensional array. In a special case is the matrix, which has 2 dimensions. And so, you know, we often create matrices this way. Yeah. So you can take something, let's say x is this atomic vector 1 through 20, and you can, if we ask the dimensions of x, and right now it's null, I think I can just do 4, 5, okay? And so this means it'll have 4 rows and 5 columns, and x is now a matrix, okay? The other way I could have done this is I could say matrix 1 through 20, n row equals 4, okay? And that will also create a matrix that way, all right? But you can just basically take a, let me just try this again. 1 through 20, so I've got atomic vector. If I take the dimensions on this, again, there's no dimensions, but if I take the dimensions and I say, okay, for the dimensions of y, let's, we can try something where it'll complain, okay? We can say 3 rows, 7 columns, okay? It produces an error because it says, okay, this should have 21 elements, but y only has 20. So, you know, what are you trying to do? So, we have this instead, okay? But again, the way the matrix works is it fills them column-wise, okay? And so if you wanted it to go the other way, so here it goes 1, 2, 3, 4, 5 down the column. If you wanted it to go the other way, when you create your matrix, okay, you would have to do something like matrix 1 through 20, and then you do n row equals 4 or number of columns equals 5, whatever. You don't have to explicit, it will figure it out, but then you have to do by row equals true, okay? And then it fills it out that way. All right. 1, 2, 3, 4 rows, 5 columns, and it fills it out by row. Okay. Something happened. The one thing to note is what if so here I have x. It's a 4 by 5 matrix. It's filled out by column. What would happen if I did x plus 10? Yeah, it would add 10 to every single element, right? Okay. What if I did x plus 10, 20, 30, 40? What would happen here? Okay. So what this does, so again, keep in mind x is 1 through 20. Effectively, it's recycling 10, 20, 30, 40. So it adds 10 to this everything, 10 here, 20 here, 30 here, 40 here, and then it comes around and it recycles, and it goes 10, 20, 30, 40, 10, 20, 30, 40, so on and so forth. Okay, and you can do this, and it will you know, maybe you wanted to do 10, 20, 30, 40, 50, okay, and it adds them. The way it recycles is it goes up and down the list, right? What would, you know, what if I wanted to do, I wanted to add 10 to the first column, 20 to the second column, 30 to the third column, 40 and 50, you know, to the fourth and fifth columns. How would I have to do this? Yeah, so this gets complicated. Effectively, you would have to transpose this matrix, okay? You would transpose this matrix, add them, because this is an inherent thing of R, and it's in the way it handles matrices is it does it column-wise. So you would transpose it, add the numbers, and then transpose it back, okay? So you would want to do something like, okay, we're going to transpose X, we're going to do all of the addition, and then we're going to transpose it back, okay? And then so we wrap a transpose around the entire thing, okay? And that way it does kind of what we wanted it to do. Okay, so these are just things you got to keep in mind in terms of the way R handles its stuff. Okay, does that make sense to everybody? That we're transposing it, adding them column-wise, and then transposing them back if you want to have things added basically by row. Okay, we don't have there's not a, you can't tell R, oh, this time when you recycle by row. Okay, recycle by row. That's not something we can do. Okay, but you know, you just think a little creatively and you can get it. Okay. Array is just a three-dimensional extension of basically a matrix. So you have the elements 1 through 12, okay? And then the way it fills out is it fills first by the you know, the first dimension, then the second dimension, and then the third dimension. So it goes 1, 2, okay, 3, 4, 5, 6, and then the third dimension goes 7, 8, 9, 10, 11, 12. Okay, so you can think of this as kind of a three-dimensional array where you have basically a two-dimensional matrix in front of another one. Okay, and so and it kind of indicates as such using this comma notation. I don't know if the array makes sense. For some of us, visualizing an array is easier than others, and that's okay. So if I want to make an array, let's do I don't know, 3 times 3 times 3 would be 27, right? So let me just yeah, we'll do 1 through 27, and then our dimensions are 3 by 3 by 3. Okay. And then so here, you know, I've got a 3 by 3. So this is kind of like, you guys remember 3D tic-tac-toe? So it's kind of like that, right? And then so you have, you know, the top 9, and then the middle layer, and then the bottom layer. Okay. And you can, you know, arrays. So, and as far as our brains go, we can only imagine things in 3 dimensions. But I mean, there's no limit to this. I could add a 4th dimension, okay, and it just looks crazier, but and it just says, okay, so now you have basically your first 3-dimensional 3 by 3 by 3, okay, and then you have now we're changing this second thing, and it goes, the second you have your next 27 elements, and then you have your third 27 elements, okay? And because your screen is 2-dimensional, it can only display 2 dimensions, and then all of the other dimensions just get displayed using this comma notation, okay? And so if you want this particular if you want element 68, okay, how do I reference that? Okay, Well, I would have to do Z using bracket notation. I want the second row, second column, second grid in the third cube, okay? And then that would get me 68, all right? Or, you know, and if you leave off any of these things and you just say comma, comma, then, whoops. Oh, yeah, that was not what I expected. You know, this pulls the second row, second column from all of the different things, okay? So it's you know, if you wanted this thing, you know, you can reference it as such, okay? We're not so good at visualizing things in our head in things higher than 3 dimensions, or I don't know, maybe some of you are. You can imagine what do they call it, a tesseract easily, and you know, and it's like folding in on itself, and you're like, oh yeah, A Wrinkle in Time. I totally got that book. Never mind. So we have this, okay? Nobody read A Wrinkle in Time? Madeline and Engel, yeah, right? And they're like traveling across. Anyway, huh?
What are arrays mostly used for?
What are arrays mostly used for? For whatever, like, huh? What's that? Returning complicated objects? I'm so sorry. Okay. When do we use arrays? There are occasions where you're doing, I don't know, matrix operations, but you want to keep track of things in maybe a third dimension. So perhaps, you know, you're taking a bunch of measurements in a rectangle, but then like over time, you're going to take the exact thing, and you can have a third dimension for, you know, time 1, time 2, time 3, or something like that. It's just an option as far as the availability in keeping track of these things. So I would say they're a little bit less commonly used, but it certainly still exists. And calculations with matrices in R is pretty fast. Okay, the underlying calculation system for doing math, it's very good if you can put things into vector form, or as an extension matrix or array form, rather than, you know, later on we'll talk about loops, and loops are fine, and it's often easier for our brains to think about loops, but if we can vectorize or make our codes into matrix form, we'll have some speed advantages there. Okay. Okay. I think I already demonstrated this. You can modify an object in place, so you just by using the dimension attribute. Okay. And so you just take a vector 1 through 6, and you say, hey, I want to apply some dimensions to this thing, and it does that. Okay. And you can say, oh wait, never mind, I meant it the other way, and it modifies that thing. So you know, we have the length function. Okay, what would happen if I put in length of z? Or let me just show you. Okay, so we have x and we have y. Okay, z is 4-dimensional array. Let's ignore that. Length of x. What would length of x give me? It would return back 20, right? There's 20 elements total in x. It says we got a length of 20. Okay. If we want to know how many rows or how many columns we have, we can also say the number of rows of x, the number of columns of x is 4, and we have 5. Or you can ask the dimensions of x. Okay. And then we also have names, row names, and column names. Okay. So if I say names in x, it doesn't say anything, or row names of x, these things don't currently exist. Okay, but we can assign these. All right, so if I wanted to do column names of x, we can say I want A, B, C, D, and E. Okay, and then so now when I print out X, I've got little column names here. Okay. And now I can refer to columns by name. I don't think this is this allowed. Yeah, this is not going to be allowed. Okay, because the $ notation only works for lists. This it doesn't work for a matrix. All right, so you can kind of subset that way. We'll talk about subsetting in the future there. All right. And then so now if I say what are the column names of X, it reports back this. If I still ask row names of X, it returns null. I would say in general we don't really like to use row names. There's nothing wrong with having row names, but you know, if you're dealing with a data frame, you can store the row names in the data frame itself, right? I would say the only time you want to assign row names is if you're dealing with a matrix that's strictly, or your data is strictly numeric, and so you can keep it in a matrix, because in a matrix everything has to be of the same type, right? They're essentially atomic vectors with a dimension attribute attached to it. So everything has to be the same type. And for whatever reason you want to keep track of these different things, then I suppose you can use row names. But in general, we don't often use row names. I think there's a few. I want to say cars is no, cars is MT cars. I don't know. So MT cars is a built-in data set. Motor Trend cars. No, it's still a list. Okay. But for whatever reason, they use row names of MT cars rather than storing. This could have been a matrix, because they're all numeric types. I guess these are integer types, but no, they're all doubles. It could be a matrix using column names and row names, but in general, we don't necessarily avoid row names, but I would say we don't use them as often. Okay, row names generally stored in the thing itself. All right, so length, number of rows, number of columns, that is all available to you. Okay, B is the array, and it looks like that. Okay. You could assign names to a three-dimensional structure this way using dimension names. Okay, and again, maybe a little bit less common. Okay, we can combine matrices and arrays using cbind and rbind. Okay, and then you transpose a matrix with T. Okay, you can test an object to see if it's a matrix array using is.matrix or looking at the dimension. Okay. And then so if we have, again, let's say A is 1 through 20, and then we'll say dimensions of A. Okay, so if we have this, I can cbind A, and they bind them just column-wise. Okay. Rbind, on the other hand, just basically glues, one on top of the other in terms of the rows. Okay. Rbind, cbind, and rbind. Okay. You can have one-dimensional matrices. Okay. So let's just do this again. A is so here A is a vector. Okay. and if I ask the dimensions of A, it says null. Okay, I could turn this into just one row, 20 columns, and this is it's a matrix, and then and it is this, right? So is.matrix A, that is true, whereas just if I do 1 through 20, that's not. Okay, so it's still a one-dimensional structure. Sometimes things get pushed into matrix form when you do some multiplication and things like that. It's gonna result in matrices. So it says they may print similarly, but will behave differently. Okay, and so t-apply and different things will reveal this stuff. Okay, so structure A. This will tell you, if you look at the structure of A, it is because it says 1 comma 1 through 20. This indicates to us that it's a matrix. Whereas if I just say structure of 1 through 20, you don't have this indicate. You only have a single dimension there, so you can tell that it's a vector there. Even though when you ask for the structure, it looks very similarly, because there's the comma here to indicate that there's two dimensions on A. You can tell it's a matrix. Okay, a one-dimensional vector versus all of this. Okay. All right, I just kind of skipped over that quickly, but I think it's fine. All right, and then data frames. Okay, so matrices, again, those are atomic vectors with a dimension attribute. That's essentially what a matrix is. Calculations go quickly. Data frames is a list, and so you can have different types of data stored in a data frame. And I think you guys are very familiar with data frames, and it's just that everything in the list, they all have to have the same length. Okay, so you get a rectangle. So you can have, a list of 5 things which are going to form your columns, and all 5 of those things, they need to have the same length so that you get a nice rectangle shape there. Okay, so this means that a data frame has names, column names, and row names. Names and column names are the same for data frames. And so, and this time, the length of a data frame is the length of the underlying list. Okay, so it's the same as number of columns. And it's going to behave very much like a list. So here we can create a data frame, and you use the data.frame construction, and you can say x is 1 through 5, and y is the first 5 letters. Okay, you guys are familiar with just these 2 built-in vectors, letters and letters. It's basically A through Z, and so and rather than, so earlier I wrote A, comma B, comma C. Like if you want to quickly name things this way, you can do it that way. You can also just say letters. I want 1 through the first 5, the first 2, or whatever. You can say the 10th through the 15th or something like that. Okay. And then so there's lowercase letters and then all caps letters, which is another the capitals. Okay. So anyway, so I've created data frame df this, and so this is just x is the numbers 1 through 5, and y is whoops, I called it df. Okay. 1 through 5 and A through E. Yes, question?
I was wondering, are you covering data tables? Or the package data tables?
Data table? I'll give him a shout out later on. I'll cover package dplyr, which has its own thing, but then yeah, data table, it's one worth mentioning. Okay, but they're effectively data frames with just a little bit of a, I don't know, extra features, I guess. Okay. Okay. Again, if we ask type of for df, it's going to say it's a list, whereas if you ask class, it'll say it's a data frame. Okay. And you ask the structure of df, it's a data frame, but really it's a list, and it's got the integers, and then it's the kind of the default setting for data frames is to turn things into factors. Okay, so df $y is actually it's treating it as a factor and not a character vector, which is fine. Okay. All right, and then so if you don't want to turn them as factors, you got to set strings as factors equal to false. Okay, so earlier we created the data frame here. If I wanted this strings as factors, I can set to false, and we can ask the structure of this, and now it's a character vector. Okay, so depending on what you want, this is probably a good thing. Strings as factors false, but perhaps you want something else. Okay, again, stored as a list. You can ask, is it a data frame? The class is all of that. You can coerce things into data frames. All right, and these are the things that will happen. So if you coerce a vector into a data frame, you'll get a one-column data frame. Okay, and then a list will create one column for each element. Okay, if that list, if the different elements in your list aren't of the same length, right? So if you got list item A is a vector of 10 items, and list element B is a vector of 9 items, it's gonna error out. Okay, and then a matrix will just turn into a data frame, right? So here, so here's my matrix A, B, C, D, E. So this is, right, if I say type of X, it's a matrix integer. Okay, class X, it's a matrix, and I can do s.dataFrame X, and now it's a data frame. Okay, and they look almost exactly the same. The indicator that things has changed is that we no longer have the matrix notation to subset the things. Okay, and so if I'm going to call this G, okay, class of G is now a data frame. G looks like this, and type of G is now a list, and the structure of G, it looks like this now. Whereas the structure of my matrix X is it's a matrix, right? Okay, and so when you coerce them, you'll get the same number of columns and number of rows. If you have names attached to that matrix, they'll be preserved. Okay, whereas I think Y is a matrix, there's no names here, and if I do as.dataFrame here, it just assigns the names v1, v2, v3, v4, v5. Okay, rather than because there were no column names to preserve here. Okay, cbind and rbind work the same way for data frames. When you rbind or data frame, you got to make sure that your column names line up. Okay, otherwise it'll get angry with you. So when combining column-wise, number of rows must match, row names are ignored, all of this. Okay, so this is an important thing. It's a common mistake to try to create a data frame by c-binding vectors together. That's not going to work because c-bind, general, when it takes vectors in as output, it's going to try to produce a matrix. Okay, so if you want to create a data frame, just use the data.frame and then stick the vectors in there. Okay, and that'll work. Okay, see you guys. So.